All right, so what we're going to do now is look at Bitwise Operations. Bitwise Operations is a concept that you will use not only for your logic class, but also in programming classes, and I've used it a lot in real life as well. It's a powerful concept. You're able to handle data, large amounts of data. You're able to get what you need and ignore the rest and be able to set bits. And I've used it actually to make simple encryption algorithms as well. Is just so people don't open up a little file and be able to see what I'm talking about. They'll see gobbledygook instead of the actual data. It's not a really secure method of encryption, but anyway, we'll talk about that and we'll see what we have. I want to start off here by using this little example. We have A naught and B naught is equal to Z naught. A very simple logic equation, something that you're all used to. And if we were to look at what happens when we do that, if you say A naught is 0 and B naught is 0, then Z naught is 0 and Z1 0, and A is a 1 and B is a 0, 0. And when they're both 1s, we get a 1, right? Basic logic, nothing new here. What I want to do though is I want to turn the A naught and B naught like this, like we used to do in grade school. There you go. So we say A naught and B naught equals Z naught. So it's the exact same equation as this, but now we've just written it like this. Why would I want to do that? It's because I want to put more digits there. I want to say, how about if we have A and B equals Z? And both of those A's and B's and Z's, all three of those are 4-bit numbers. So that this would be A3, A2, A1, A0, and B3, B2, B1, and B0. And all that equals Z3, Z1, Z2, Z1, and Z0, like that. So if this is what we're doing with our bitwise operations, that means that A naught and B naught equals Z naught. That's an equation by itself. And A1 and B1 equals Z1, equation by itself. When we did the adding, there was some carry and stuff like that, but here, nothing. It's just straight logic. A2 and B2 equals Z2, and so on and so forth. Let's do an example, and maybe it'll make sense. So let's say let's let A equal 1, 0, 1, 0, and B equal 1, 1, 0, 0. So if we and those things together, we're just going to say 0 and 0 is 0, 1 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1. Oh, sorry, there you go. Now, why do we, what can we take from that? Well, there's two parts to the circuit. This is our data. Let's call this our data. And if so, then this is our mask. And that means that we're taking anything that's ANDed with a 0 and we're going to force it to be 0. So that means those two are zeros. The part that is not masked off, that's called the masking, is when you have the 0 and 0. You've masked that off. This here is this. So we are just saying ANDing this with 1, ANDing this with a 0, and so you get 1, 0 down here. And that's it. So you can keep part of your data and you can force everything else to be a 0. If you do a larger number, we can see this pretty clearly. So if we say 1, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1. And let's mask that with, let's say 1, 1, 1, 1, 1, 1, 0, 0, and 0, 0, 0, 0. Well, anything ANDed with a 0 is going to be a 0. So immediately I can say those 4 are zeros, and actually those 2 as well. These two, it's just going to be 1 and 1 is a 1, and 1 and a 0 is a 0. And then we have those 1, 1, 0, 1. So what we have done here is we have taken these right here. They are directly mapped down. Those are 1 for 1, the same thing, whereas everything else is a 0. That's called masking, and it's just the simple AND term whenever we apply it to more than one bit at a time. So we can do the same thing with the OR term. where we're going to set things. We're going to force things to be a 1, and then we're going to pass through other things. So for instance, if we take our 1 0 1 0 and we OR it with 1 1 0 0, well, anytime there's a 1 anywhere, 1 1 1 0, we're going to get 1s. So 1 or 1, 0 or 1, 1 or 0, 0 or 0. That means that we were forcing those 2 bits to be a 1. These 2 we pass through. Again, with our bigger example where we had 1 1 0 1 and 0 1 1 0 and 0 1 1 1, and we had 1 1 1 1 1 1 0 0 0 0 0 0. In this instance, anywhere that there's a 1, there's going to be a 1 down here. So we're going to just put 1 1 1 1 1 1. This one also has a 1. This one's a 0, a 0, and then 1 1 1. And that's all the digits we got. I got a little extra thing there. All right, so what you can see is that we forced those to be a 1 here. And then everything else just passed through. Those were just pass-through values. They were the same as those. So that's setting a bit. Now, the next one is our exclusively ORed, is when we're toggling it. So we toggle with an exclusive OR. So first off, the first one was an AND. This was AND. This was OR. And now we're doing XOR. And if we look at the XOR, 1 0 1 0 and 1 1 0 0, and we're exclusively ORing those things together, well, let's see, 0 0 0 1 1 0, so that's a 1, and 1 1, that's a 0. So the zeros in this instance are again passing through like the OR was, but the ones, they're actually changing it. It was 1 0, now it's 0 1. So that's exclusively OR actually toggles. By the way, if you take 0 1 1 0, which was our answer here, and we toggle it again with 1 1 0 0, the same thing we had toggled it with before, what do you get? You get 1 0 1 0. So you get your data back. That was this answer right here. So you can use that, like I said, as a really, really simple encryption. It's not it's just a way to hide your data. It's not really a safe encryption. It's just a fun way to be able to make your data look messy. But as long as you have the exclusively ORed bit there, you can do a pretty good job of messing up the data so it's unrecognizable. All right, and that's our 3 types of bitwise operations that we're going to cover: masks or resets, because we're forcing things to 0, sets with the OR, and XOR to toggle.